In this class, we're going to talk about the tie breakings in the simplex method. So, in step 1 of each iteration in the simplex method, we choose the non-basic variable having the negative coefficient with the largest absolute value in the current equation 0 as the entering variable. But cases may happen when there are 1 or 2 or more non-basic variables having the same largest negative coefficient. Then in this case, we say that the choice between these contenders may be made arbitrarily. So the optimal solution will be reached eventually anyways, regardless of the tied variable chosen. And at this point, there is no convenient method for predicting in advance which choice will lead there sooner. So this is first. If we have a tie for the entering basic variables, we can choose the variables arbitrarily. Second, we say if in the minimum ratio test, which is the step 2 of the iteration, 2 or more basic variables tie for being the leading basic variable, does it matter which one is chosen? Theoretically, it does, and in a very critical way. First, all the tied basic variables reach 0 simultaneously as the entering basic variable is increased, since they have the same ratio as the entering basic variable increases. Therefore, the 1 or 1s not chosen to be the leading basic variable will also have a value of 0 in the new BF solution. And at this point, we say a basic variable, because it's not leading, with a value of 0 is called degenerate. Second, if one of these degenerate basic variables retains its value of 0 until it's chosen at a subsequent iteration to be the leading basic variable, the corresponding entering basic variable must also remain 0. The reason is that in the simplex method, we need to increase an entering basic variable so that the leading basic variable will decrease to 0. However, at this point, the leading basic variable is already 0, so the entering variable, which was non-basic and takes value 0, cannot be increased any further. Consequently, since the entering basic variable and the leading basic variable both retain the value of 0, the value of z must remain unchanged. Third, if z remains the same rather than increase at each iteration, the simplex method may then go around in a loop, repeating the same sequence of solutions periodically rather than eventually increasing z toward an optimal solution. In fact, examples has been artificially constructed so that they do become entrapped in just such a perpetual loop. Fortunately, we say although perpetual loops are theoretically possible, it has rarely been known to occur in practical problems. If a loop were to occur in a practical problem, one could always get out of it by changing the choice of the leading basic variable at the very beginning when we encountered this problem. Furthermore, special rules can be constructed for breaking ties so that such loops will always be avoided. So practically, if we have two tied leaving a basic variable, we can just break this kind of tie arbitrarily and proceed without worrying about the degenerate basic variables. Next, we consider a case in the tabular form that if every coefficient in the pivot column excluding equation 0 is either negative or 0, then the simplex method fails, because to choose a leading basic variable, we want to compile the minimum ratio of only the positive coefficients. This result actually means that the objective function z would increase indefinitely, thus z is unbounded, and there is no optimal solution to the problem. Practically, if there is no optimal solution, this means the model may have been misformulated, either by omitting some relevant constraints or by starting them incorrectly. Alternatively, a computational mistake may have occurred. Let's look at an example. If we consider this linear programming problem of maximizing z equals 3x1 plus 5x2 with the constraint that x1 plus x3 equals 4, well, here we already introduced the slack variable. If we build up its simplex tabular, we can see that in the first optimality test, -5 has the biggest absolute value that is a negative coefficient. However, corresponding to that pivot column, there is only one coefficient below, that is the coefficient of 2, 0. And then we say in the minimum ratio test, we need to compare the ratio of the right-hand side between and the positive coefficients in the pivot column. But there is no positive coefficient here, so there is no minimum ratio test, and then we cannot choose which variable is leaving. So in this problem, we say z is actually unbounded and it has no optimal solution. Or we can see this conclusion from our objective function. Our objective function contains 5x2, but in our constraints, there is no upper bound for x2. We only say x2 has to be non-negative, so it can be increased indefinitely. So x2 can go as far as possible, so our objective function z will not have a maximum value. It will not have an optimal solution. Okay, so the next problem is that if in the final simplex tabular, at least one of the non-basic variables has a coefficient of 0 in equation 0, then increasing any of such variables will not change the value of z. So this means that the problem has more than one optimal BF solution. In the process of the simplex method, it automatically stops after one optimal BF solution is found. However, if we want to find other optimal BF solutions, we can perform another iteration of the simplex method. And in this new iteration, we simply choose a non-basic variable with a 0 coefficient as the entering basic variable and proceed as what we did in the simplex method as usual. Here, in fact, any linear programming problem with multiple optimal solutions has at least 2 CPS solutions, counterpoint feasible solutions, that are optimal. Every optimal solution is actually a convex combination of these optimal CPF solutions. Here we define the convex combination of two vectors. If u and v are two vectors, then the convex combination of these two vectors is defined as t times u plus 1 minus t times v, while t is a constant between 0 and 1. From this fact of the CPF solutions, we actually say that in the augmented form, every optimal solution is a convex combination of the optimal BF solutions. Let's look at an example. Here, we want to maximize the objective function 3x1 plus 2x2 with all these constraints. So we can start our simplex tabular as usual. We first build up the tabular and then do the optimality test. Equation 0 contains two negative coefficients. We pick the biggest one, -3. This is our pivot column, and then do the minimum ratio test. 4 to 1 is 4, 18 to 3 is 6. So 4 is smaller, and then we choose this row as our leaving basic variable x3. So then we do Gaussian elimination to make that column unit, meaning we only want to keep this one and make all other coefficients 0, and then we have a tabular. In this tabular, again, we apply the optimality test. There is a coefficient in equation 0 being negative, so this is our pivot column, and then apply the minimum ratio test. We choose the leaving basic variable, and then do the Gaussian elimination to make that column unit 0, 0, 0, 1. Now, once we have this simplex tabular, we say that, well, we have the basic variables x1, x4, x2. However, in this table, we have x3, which is non-basic, has the coefficient in equation 0, 0. This means increasing the value of x3 will not affect the value of our objective function. So this model has more than one optimal solution. And then to obtain another optimal BF solution, we can choose this column as the pivot column because x3 now has the coefficient 0 in our objective function. And then again, repeat the minimal ratio test. Pick the positive values, compare their ratio, and then pick equation 2 as our leaving basic variable x4. And then repeat the Gaussian elimination so that we make that column unit. After doing that, we can actually see that we obtain another set of BF solutions that is optimal. In these tables, we can read separately from the first table the optimal solution and the value of the objective function that can be read from the right side directly. Or in the second table, we can read from the right side of the optimal solution and then the corresponding objective function. The objective function value are the same, but these two optimal solutions are different. They both are optimal BF solutions because there are two values, 0, and then three values, non-zero. So this simply means that we have two optimal BF solutions for the linear programming problem, and then any convex combination of these two solutions will also be an optimal solution to the problem. Geometrically, what happens here is that if we draw the feasible region of our linear programming problem, we see the points 2, 6 and 4, 3 are two CPF solutions, optimal CPF solutions. And then the convex combination of these 2 points is actually the line segment between these 2 points. So what it says is that if we have 2 optimal solutions, then the line segment between these 2 points is also every point on the line segment will also be an optimal solution to our original linear program problem. This is because if we look graphically that the slope of our objective function actually matches the slope of one of our constraints, so that every point on this line segment will give us an optimal solution. Okay, so at the end, for future references, we will introduce briefly the matrix representation of the simplex method. So we say that in the past, we just use systems of equations and then the coefficients variables to record the linear program problem. However, if we simply write all the coefficients and the variables as vectors, we can have its matrix form. In the matrix form, we simply have our objective function as a product of 2 vectors, c and x. Here, c is a row vector that consists of all the coefficients. And x, the capital X, is a column vector that consists of all the variables. And then the coefficient matrix A simply is the coefficients of all the variables in our constraints. And then B is simply the column vector of all the constants on the right side of our inequalities. And then, of course, we say we have a linear program problem in the form of less than or equal to. We can introduce slack variables to make all the inequalities equations. And if we introduce a column vector of slack variables, we also have the equation form of our linear program problem. And then the augmented coefficient matrix will simply be our old coefficient matrix A with the coefficient matrix of the slack variables, the identity matrix with zeros and appropriately assigned. And then the column vector of variables combined with our original vector x and then the vector of slack variables xs equal to our right-hand side, the constants b. So in summary, we say that we can express our simplex tabular in terms of matrices, and each part of the matrix represent either the coefficient, the identity matrix, the select variables, the right side. So we'll put the table here, and we'll come back to this table to see how it can be used for future study. So this is what we have for this class.